This is Steve N4LQ, and we're going to talk about multiband antennas today. And wouldn't we all like to have an antenna that covers all bands? So we're going to talk about the different types of multiband antennas, and we're going to wind up talking about the newer models of the end-fed half-wave antenna, and we'll do some comparison. We've got several common antennas here, and these are all multiband antennas of one sort or another. This is probably the most popular and has been for at least 100 years, the open wire fed antenna. And it's simply a length, any length of wire that's fed in the middle by a balanced line or ladder line. The antenna can be a half wavelength long on the lowest band, or it can be a little bit less, or it can be a lot more. The length is not really all that important. What's important is that you have a tuner at the end here that can match this thing up to your transceiver. The impedance at the center of the antenna is going to vary all over the map, anywhere from 5 to 5,000 ohms. It's a little bit crazy, and that's why we have to use super low loss feed line in order to not lose a huge amount of power. Now we can use window line, which is fine, except when it gets wet, it tends to be considerably lossy. So I prefer this type of line, and I've used these antennas many times, and they are really wonderful. The antenna is supposed to be balanced. That means that the antenna should be level. If one side is closer to the ground than the other, we end up with some radiation from the ladder line, and that's because the feed line is supposed to have currents in them that are 180 degrees out of phase. If we have an unbalanced situation, then that will make the phase between the two something other than 180 degrees, and we won't get radiation cancellation. And so we will pick up signals and noise on the feed line if the antenna is not perfectly balanced, and they almost never are. But we do the best we can. And then the tuner or matchbox has to have a balanced output, and if it does not, we'd have to use a balun, preferably a current type balun, in order to keep the magnitudes of the two currents identical. If the antenna is unbalanced for some reason, like I said they usually are, then the tuner will actually burn off the excess current in one leg and keep the other leg the same, so you end up with the same magnitude of current in each line. Yet that does not stop the radiation, because the radiation is caused by the phase angle not being 180 degrees, and there's not too much we can do about it. So losses occur in the tuner, which could amount to maybe 10% at the most, and in the balun. So there's the one of the downsides to the system. And of course also we have to make readjustments every time we move within the band and when we change bands. So it's a lot of knob twisting and switch flipping. The W8GZ Wyndham, which came out in 1936, is a single wire fed antenna, and it never gained a whole lot of popularity, and eventually morphed into this thing here called the off-center fed dipole, or the Coax fed Wyndham. Later on it became the Carolina Wyndham, and the theory is that somewhere along this antenna there'll be a impedance on several bands that we can match with a balun that has a 4-to-1 or 6-to-1 ratio. And then there's a never-ending string of articles published over the year that says the balun should be here, or it should be here, or here. and it never ends. But anyway, it's a compromise wherever you put it, and the SWR on the feed line will be fairly reasonable on at least 3 or 4 bands, and it's a handy antenna to use in those instances where it matches. The radiation pattern on all of these antennas is going to be random because as we change frequency, the pattern of our antenna changes. On the fundamental frequency, for instance, if this is an 80-meter antenna, it's going to be broadside, and as we go up in frequency, it tends to start to come off of the ends. The next antenna is the fan or parallel dipole, and this is simply a bunch of dipoles for different bands connected in parallel together here in the center, and they are kept evenly apart, we hope, by these spacers. So it takes a separate dipole for each band, and we end up with quite a bit of weight and a little bit of sag there, and of course it could be a bit unsightly in your yard. It's tricky to adjust to try to get the SWR right on each band because these things interact, and you can get one trim for one band and then the next one gets messed up. So it's but anyway, it's an efficient antenna once you get it set up correctly. And note the weight here is already making our photograph start to sag. You can put it up with one support in the middle and drop your dipoles down like a maypole if you want. And you have to drop your coax straight down and then come down on the ground with it, because that'll tend to put some RF into that coax. It's nice because the directivity is predictable. It will always be broadside because these are dipoles. The trap dipole has pretty much fallen out of use. It required a set of traps for each band, and these act as like blockers to keep one band from operating into another. For example, if this is a 20-meter trap, then 20 meters, if you transmit 14 megahertz into this antenna, this trap will stop it from going any further. So it more or less cuts the antenna off right there. And then if we go to 40 meters, maybe this trap, these two traps here, will stop anything from going past this point. So you need a set of traps for every band, and each trap will have some RF loss as the antenna current goes through it. And sometimes they're made out of a capacitor and an inductor, and sometimes the capacitors will pop on you and you have to replace them. And they're a little bit heavy and a little bit unsightly, so they're not very common. Of course, there are lots of trap verticals now, and they work pretty well. The G5RV started out being a 20-meter antenna back in the 1930s. I believe it was Mr. Varney invented this thing, and he wanted an antenna that operated on 20 meters that had a four loaf, a clover loaf pattern, like sort of like a 2 figure-8s crossed, and to get worldwide coverage. And to make this thing work right, he had to put a matching section on here, 300 ohm ladder line or TV lead-in wire. Anyway, it's great for 20 meters. The SWR is pretty good, and then somebody later on decided to try to make it work on every band by using a wide range tuner. And the SWRs, they're not astronomical, but they're still fairly high, especially on 80 meters. And even on 40, it's like 5-to-1. And so unless your coax is very heavy and very short, you're going to have a lot of loss. So I don't recommend this one. This one is better, the ZS6 BKW antenna. And it's a little shorter than the G5RV, but the length comes out such that the SWRs are better on all the bands than the G5RV is. Still pretty high on 80 meters. 40 is great. 30 is not usable. And I don't know about 17. I suspect it's not very usable either. So it gets you on several bands, but not all of them. This right here is the linked dipole, and it's just a bunch of insulators that have jumper wires across them. So for every band, you would measure down for, like, this one would be like for 10 meters. And so you'd measure down about 8 feet and put an insulator there, and then another one for 20 meters and another one for 40 meters and then 80 and so forth. And you can put as many as you want on there. So every time you change bands, you go outside and lower the antenna down to the ground and move your jumper wire, and presto, you have a dipole for that particular band. Not too handy for the homeowner, but they're fairly popular in use for portable use. And you can imagine going out, get out of your tent and go out and lower the antenna and just changing bands by moving a couple of jumpers and then pull it back up. So it's pretty good for that. It's an efficient antenna. It doesn't have a lot of power loss because, after all, it is just a simple dipole. The loop antennas, two types, the vertical or delta loop and the horizontal loop. The vertical loop is a full, well, actually both of these are a full wavelength in diameter on the lowest frequency. This one is shown here is a 160 loop, or you could make it for 80 or even 40, but it's got to be a full wavelength. So for 80 meters, for example, you would take 1005 and divide it by the frequency in megahertz, and you'd come up with about 270 feet in diameter. And the same for the vertical loop. The nice thing about these antennas is the feed point impedance is not real high. It's usually around 100 up to about 400 ohms. So it makes a decent match for ladder line, and it makes it easy to tune. The radiation pattern on the vertical loop would be low on the low bands, so it would be a good low band DX antenna, but on the high bands, the radiation angle tends to be very high, going straight up, and that's just the opposite of what you need. So it'll work on all bands, but this will work best on the lower bands. This one, the radiation angle on the low bands would be really high, which is fine because you might want to use this for local nets going out to maybe 500 or 1,000 miles. For DX, this one would be better on the low bands. Now on the high bands, this one tends to have a low angle radiation, just the opposite. So it's good for DX on the high bands, but not on the low bands. Now the one factor that people don't usually talk about is there is a lot of directivity with this antenna on the higher bands. It's very directional in a direction opposite the feed point, so it would go like this off the far end. So that's sort of rhombic antenna-like, and that's great if you're wanting to talk to somebody out there in that direction. If you're on the East Coast, you might want to aim this thing west, cover the entire United States. Pretty nice for that. And then you've got lots of little lobes coming off around the antenna, and but the majority of the power is going to go off that way on, say, 20, 15, and 10 meters. Again, it's easy to load up. The disadvantage is it takes more supports. You can get by with 3 and turn this into a triangle if you want to. All right, then these two antennas are random infed antennas, and they're made out of a random length of antenna. And this one is fed directly with the tuner, so basically you just open your window, throw the wire out, and hook it to a tree. You might want to put some counterpoise wires out on the ground, and the same for this one. You know, these are compromise kind of inefficient antennas, good for temporary use. This one right here really annoys me because they make a lot of promises, and there's a lot of hype about this so-called 9-to-1 unun. It's called a magnetic unun, and there's names for the antennas such as the QSO King and the Ultimax, and you know, they're all over eBay for all kinds of prices, and they all come with recommended lengths for the antenna wire, and the idea is to try to avoid a resonant length so that it presents a reasonable match to this unun and doesn't have a huge amount of power loss. So it's usable, and you'll get a lot of contacts with it, but it's not the best, that's for sure. So the end-fed half-wave antenna started out in 1909 being used for hydrogen-filled balloons. Mr. Hans Bigelow actually has a patent. You can look it up on the web. And this is his drawing in his patent. And number 4 here is a half wave length of wire hanging down. So there's your end-fed half wave. And this pair of wires here, your ladder line, is your feed line, and it has to be 1/4 of a wavelength long. It acts as a transmission line transformer, and it transforms the high impedance of this end-fed half wave to a low impedance so that it matches the transmitter more easily, and that gets the high voltage away from the hydrogen-filled balloon, which would seem like a good idea. So what is an end-fed half-wave antenna? Well, an end-fed half-wave antenna has to be a half wavelength long on the lowest band that you're going to use it. So if you're going to use an antenna on 80 through 10 meters, it must be a half wavelength long for 80 meters. And you calculate a half wavelength, as you know, by dividing 468 by the frequency in megahertz. And so for 80 meters, we would be in the neighborhood of 130, 135 feet. We feed it on the end. The antenna can be vertical, horizontal, and of course it can also be bent, not too severely, but it can be bent. It can be tuned and limited to a single band. And that's the way these all used to be. Hans Bigelow's antenna was. You could not change the length of the antenna without changing the matching. There are antennas that use parallel LC networks to do the matching, and that would be like the PAR end-fed antenna. In that little black box of his, he's got a tuned matching system that is a parallel LC network. And that of course would only be good for one band, and you'd have to have one for every band. And then of course you could just feed it with ladder line on the end and try to use a tuner on it, but that would be a horrible solution because the ladder line would radiate like crazy once you got off of the design frequency. And the last solution is to feed it with a broadband high impedance transformer for multiband use. That's what we're going to look at now, and that is the preferred way to feed it. So we need a transformer that takes 50 ohm coax and steps it up to a higher impedance to match that end-fed antenna. So this schematic shows that. It doesn't show the core, but it does show the transformer, and the end-fed half-wave transformer is just that. It's a transformer. It's not a unun, and it's not a balun by any means, and it's not an auto transformer. It's just a plain, simple transformer. This schematic of the transformer came off of a website describing the Tesla coil or Tesla transformer. So maybe Mr. Tesla had a good idea. So this drawing right here is sort of a pictorial and an explanation of what you need to build the transformer. We got the specifications, we got some part numbers here, and we started out using a ferrite mix of 43, and then we later learned that 52 mix was more efficient. Now the mix of a ferrite core means the chemical ratios used to manufacture this stuff. I have no idea what's in it, but one thing I do know about ferrite is that it's a great insulator. So we don't have to worry about the wires shorting to the ferrite. So the ultimate transformer would have 3 of these cores stacked up, and that would use 52 mix ferrite. If you want less than 3 cores, you have to use 43 mix. You can't use 52 mix. You can use 1 core and wind it, and it will handle 100 watts. You can use 2 cores and it'll handle more power, and 3 cores it'll handle even more power, and with 3 cores you can switch over to the 52 mix, and that would be the most efficient of all the 80 through 10 meter antennas that we know of so far these days. This drawing shows 14 gauge enamel wire, and we have since graduated to 12 gauge. We found out that it actually has a lower SWR and a higher power handling capability. It's a bit harder to wind, but it's better. So here's your lengths that we use to cut the wire before we wind it. And you might want to use just a little bit longer just to be sure, and just cut the rest of it off. We have what we call the primary winding that's combined with the secondary winding for 2 turns. And note that we only count the inside turns. So we never count the outside turns. And this crossover here, we count that as turn number 8 because it actually goes down through the core. There are 3 factors that improve the performance on the higher bands, 20, 15, and 10. First, the capacitor. It is necessary. It's got to be a 100 picofarad capacitor, and it needs to be a high voltage capacitor. I would recommend using at least 3,000 volts or maybe 6,000 volts. But once you get up there over several thousand volts, it doesn't matter. They're all cheap. I've got some 30,000 volt capacitors that cost 50 cents a piece. So don't worry about cost. The voltage is not high here, but the current is, and they don't tell us what the current rating is on the capacitor, so we just use a high voltage and hope for the best, and I've never heard of any problem using a high voltage capacitor. The next thing for the higher bands is that we need to twist the primary and the secondary together, and then finally we have to use the crossover feature here. Using the crossover keeps this part away from this part down here. And if these two get close, it can mess up your SWR. So let's continue taking a look at the antenna. Here's our transformer, and this is the 80 through 10 meter antenna. And we measure out 78 inches, and here we install the compensation coil. The compensation coil compensates for the length of the antenna on the higher bands. Without it, you would have a resonant point on 10 meters up around 29 megahertz. Putting this in will bring it down to about 28.5 or so. So it's a great thing to do, and it's very simple. It's just a 1-inch piece of scrap PVC pipe with 6 turns of antenna wire around it. And we don't count that length in the overall length of the antenna. We measure from here with our tape measure up to here. And the antenna wire can be whatever you've got. Thinner wire is fine as long as it doesn't break. You can use copper-coated steel, stranded 18 gauge even, and get by with it if your trees don't sway too much, and that's very stealthy. You can spray paint this assembly here black, and maybe nobody will notice it. You can also make this antenna 67 feet long and keep this coil here in the same position, and that'll cover 40 through 10, although the SWRs will be higher. So I recommend making it the full 80 through 10 meter length. So this is our goal. Here's the inside of a transformer that I built, and this is the 80 through 10 model. 2 turns on the primary and 14 total turns. Here's a little pictorial of some wire wrapping. There's our primary and secondary wire compared. We wrap those together and we end up with something like this. And here's our cores. Here's 352 cores. These cores are 290 cores, and that's what you need for a dedicated 160 meter version. They have to be 43 mix. Super glue is used to glue these together, so we usually put a dot of glue around here like this, 4 dots, and stack them up, and it takes about 2 or 3 minutes for the glue to set, and then you can start winding. Super glue and ferrite just love each other. There's the box. There's a vent. And here we are drilling the hole for the coax jack. And this is a step drill. You can get these at any hardware store or Lowe's or Home Depot. And they're very nice for putting things like this in. One nice feature about a step drill, by the way, is that you can drill through your carpet in your house and not snag it. Makes a nice, neat hole. So this always makes a nice, neat looking hole, and you can put your coax jack on the inside and let it poke through, then drill 4 holes to mount it. Some hardware. These are all stainless steel, and I'm getting hardware from the boltdepot.com. I've got plenty of it. Don't know if I'll ever use it, but it's there. And always use stainless steel hardware so it doesn't rust. There's a 1024 bolt that I use for the stud for the ground and the antenna jack. I started out using Phillips head screws, but I found out that with the hex head I can use wrenches and get it much tighter. There's the my favorite bolt. eBay auction here, somebody had some capacitors. These are 30,000 volts, 100 picofarad, and that just shows you how cheap you can get these things. There's a spool of wire that I got from Amazon or eBay. This is 12 gauge enameled wire. It's sometimes called magnet wire. And there I am using a tape measure. And so we've cut our wire here for the proper lengths, and we've got a piece of shrink tubing here to sort of protect them, so we can now put it in the vise like so. We could use a piece of cardboard or something, I guess, to protect the wires from the teeth of the vise. And now we're going to start twisting the wires, and we've got our hands spread apart and we're pulling on it, and we're starting to do the twist. And there it comes. And we ended up like this. You can also use an electric drill if you want. You can just put these ends in the chuck, fire it up, and it'll make a beautiful, nice even tight twist. So there's our first turn. Remember, we count the passages through the center, and this is actually a complete turn. And we bend over like so, and there's our first turn complete. There's the second turn, and so forth. There's 2 turns in the center. Now we're going to start doing our secondary, and what I do is I take my thumb and I push this wire down through the center. If you try to go get the far end and poke it down through there and work it through, you're going to end up with a bunch of kinks and tangles. So I prefer doing it this way and then flip it over and grab the other end and pull it up through that way. It makes a little bit neater job. And as you're pulling it, try to keep a tension on it and bend it over the toroid, and it'll come out looking pretty good. Now, I used some previously used wire just to make this video, so forgive the kinkiness there. And there I am putting the mighty grip to it. So now we're getting ready to do the crossover, and we're poking it down through the transformer, and then we're coming up here on the other side. Note how this works. We come off the top and under and around, and we're going to start winding the other direction, and we go around and around and around until we get to number 14 here. You can count these. You'll end up with 14 total turns, and remember to count your crossover as a turn. Here's your ground wires coming off. And there it is, all wrapped up. And here is me using a Dremel to strip the enamel off the wires. I used to use a razor knife, and that works too. And so we solder our SO239 and our lugs onto the ground. This right here will end up going to the ground lug. Over here is the antenna solder lug. And so we're ready to put the thing in the box now. Takes a little bending and shaping to get it in there. Once we get it, it just drops right in there, and then we can put our bolts in and finish the job like so. So we're all done. Note the capacitor goes between the ground and the center of our SO239, and we try to make a good strong solder joint here and keep these wires short. And there's our antenna wire right here. So note that I've got a gap here and a gap here, and for some reason I like to kind of bunch these up a little closer than some people like to try to spread them out evenly. But I found that by bunching it up, I get a lower SWR for whatever reason. You can play around with it if you want. You can actually put a 2450 ohm non-inductive carbon resistor across here and connect your antenna analyzer here on your coax jack and sweep across the bands, and you'll get fairly reasonable SWRs. And as you go up in frequency, you'll see the SWR go up a bit, but as long as it's not too high, it means that you've wired it correctly anyway. But everything will change when you put your antenna on there anyway, so it's not real important. The vent, by the way, is mainly for allowing moist air to come out. And if you don't have the vents, condensation will take place inside the box, because the box will be warmer inside than it will be on the outside, and that makes the air condense on the inside. So as long as you've got some flow-through ventilation, you won't have that problem. If you just had these weep holes on the bottom, you will end up with condensation. So you've got to have a vent somewhere else to let that moist air out. Here's the nut. I used nylon locking nuts, and those things won't come loose. And use a wrench on both sides of this bolt here and really get it tight, because if you don't, you're going to end up with this thing spinning around. So here's the antenna, and again I'm showing how to measure the total length of the antenna and ignore the little coil here. I strip the wire on the end, bring it through the insulator and solder it. That's the preferred method. Some people like to leave the insulation on. That's fine, but it does skew the SWR just a little bit because the insulation causes the two wires to act like a capacitor. So I prefer to use solder. This is the compensation coil, and this is a homebrew one somebody made. Showed up on my Facebook group. We've got 9,000, 9,400 members so far to the end-fed half-wave antenna group, and everybody posts pictures of their successful operations. So somebody put this on there, and it's just a couple of holes on each end. Pass the wire through it, make 6 turns around it, and you're done. So here's a modification for 80 meters to make it work up on the phone band. And the reason the antenna has to resonate on the CW band is because if it isn't, the upper bands will be too far out of band. And there's nothing you can do about that. So what we've done is come up with a way to make the antenna work on the phone band but not affect the other bands. And you just simply cut the wire in half at the center point and put an insulator in there in your cut and solder a capacitor across it. And that capacitor needs to be somewhere between 250 and 500 picofarads. The lower the value of the capacitor, the higher up in the band it will resonate. So doing this will put you on 75 meter phone, and it will not affect the other bands. We recommend at least 1,000 volt rating on that capacitor, and of course higher is okay. This is the inverted L version of the antenna, and the nice thing about this is its radiation pattern. It gives us a combination of about everything. We get broadside, we get end-fire, we get horizontal polarity, we get vertical polarity, we get omnidirectional coverage on this part of the antenna. So it's a great all-purpose antenna. The only downside to it might be that this part may pick up some noise from your house. So we recommend, if any part of the antenna is vertical, keep it away from your house. One guy just yesterday posted that he had a high SWR, and he was actually running this part of the antenna right up against his house, and no doubt there was wiring and metal insulation or whatever inside the house that really messed it up. So keep it several feet away from the house, please, and preferably somewhere out in the yard, because it will pick up noise better than this part of the antenna. So we got a ground rod here to ground the transformer, and you can put this thing right down close to the ground, maybe a foot or so off the ground, and run your coax to your shack. This is the horizontal version of it, 80 through 10, 134 feet long. This is how mine is installed now. It's 80 feet high. I'm feeding it with coax, and my coax is grounded down at the shack. So it runs about 20 feet across the ground to the shack. It's a tremendous antenna. It covers all bands. I've got low SWRs everywhere. 17 meters gets up to about 2 to 1, but everything else is really nice and low. Here's an inverted V version of the antenna. I recommend keeping this up about 6 feet or so you can walk under it, and it will work better if you keep it up off the ground. And try to keep this angle at least 120 degrees, and the more open it is, the better off you will be. Sloper installation, probably my least favorite, but very handy for temporary use. It only takes one support, of course, and you just slope it up to the tree. You'll get some low angle radiation out that way, but the majority of your signal, the strongest lobe, will be up here, shooting up that away, up toward the stars. And that's okay too. But it's not the best. I think of the 3 or 4 different ways that I've shown here, I think maybe my favorite is the horizontal, and then the inverted L, then the inverted V, and then this one. So here we have a modification for the 80 through 10, either the inverted L or the inverted V method, where your transformer is down low to the ground. All you do is just disconnect your coax from the transformer and connect your ground wire to the coax and just leave it connected there. I'm using one of those lightning arrestor gadgets. I think it's called a blitz bug or something like that. And this is an SO239 connector. I've soldered a jumper wire here and clamped it on. So what you end up with is a 1/4 wavelength antenna on 160 meters, and your impedance is down around 30 to 50 ohms, and it gives us a nice match to the coax, and everything is happy and it works very well. The better your ground system is, the better this is going to work, but you can still make plenty of contacts with just a ground wire, or throw down some chicken wire, some fence wire or something on the ground to try to get a little bit better ground connection. But it works fairly well, and you'll get plenty of QSOs on 160. Of course, if you cut the antenna for 40 meters, then that means you can use the same idea to put it on 80 meters. If the antenna resonates too low on the 160 meter band, or actually it may come out a little bit below the band, you can simply cut your jumper wire here and put a capacitor in of this value range, and the lower this value is, the higher it will resonate on 160. And when you're done with this on 160, just unhook things, hook your coax here back to your transformer, leaving your ground wire connected, and you'll be back to where you were. And it's also possible to use a relay system to switch this. So here's a little thing about how to use the 40 meter version of the antenna on 80 meters. And again, number one here, we simply do the trick that we just showed, just bypassing the transformer. That'll put you on 80 meters. Or we can build a relay box, as we'll describe later. Or you can do this. This G0KYA published an article on the web. You can do a Google search on him and easily find it. And he put a coil down here on the end and a length of wire after it, and miraculously it resonates on 80 meters and on the other bands too. But SWRs aren't quite as good as the full-size antenna, but it does work, and it tends to be a little flaky. You have to play around with it, but it is a way to get a shorty antenna for 80 through 10 meters. This is the switch box that I mentioned that allows you to use the 80 meter antenna on 160, and lo and behold, it also allows it to work on 60 meters and 6 meters. So you can actually get 11 bands with this one piece of antenna wire, which is tremendous coverage. This is the 49-to-1 transformer. There's no ground connection. We've got a piece of coax going between it and the relay box. This relay is a 12-volt double pole, double throw relay. You can use a 120-volt relay if you want, and you can use DC to power that thing. It's going to take about 24 volts or maybe 30 to activate it. But one thing for sure is you need to use a big relay. Now, don't have a part number for you, but look for a large size relay with contacts that are far apart. A big gap is what you want. And that reduces the high voltage potential arc across here, and it also reduces the capacitance. Because capacitance is a factor here, you can just get your finger near this point here and it will actually change the SWR on the antenna. So this little bit of capacitance here between these contacts can sort of skew the SWR just a little bit. Not too bad, but just a little bit. So we're showing it here in the normal position with no power applied, and it's just simply running, it's just routing the coax straight through to the input along with the ground, which we have here, routing it to the coax jack, and it becomes an 80 through 10 meter antenna. Activate the relay, that slams these two contacts up this way, pointing up, and that connects the center of the coax directly over to the antenna, and it disconnects the ground and leaves the ground connected to the coax. And again, if it resonates too low on 160, cut this jumper and put you a capacitor like a 0.01 microfarad capacitor in there, and that'll raise the resonant point on 160. Okay, here is a photograph showing my old, this was at my other QTH, but there's my homebrew transformer, 80 through 10. This is my switch box, and there's my ground strap coming down. I've got some chicken wire over here, and I've got some horse wire going out this way about 30 feet, and some more going the other way, so it kind of formed a cross, and that gave me a decent ground system on 160, which you really need. Doesn't really help anything on 80 through 10, however. Now, if you want to make a full-size 160 meter antenna, all you need is 260 feet of wire, and your compensation coil is not needed. Your transformer is all different. It has to be size 290, and the mix has to be 43. And there has to be 3 of them stacked up. The winding ratio is different. It has to be 3 primary and 21 secondary turns. You can actually use more turns if needed to get the SWR down to the absolute minimum, depending on the height and configuration of the antenna. I've seen it well, I put one up for a guy a while back, and he had a vertical section of 100 feet, and then the rest of it was horizontal, and he ended up using this number of turns, 21. Mine, I use 30 turns because mine slopes up to 80 feet and goes horizontal for the rest of the way. And since it is so low, comparatively, it works best with 30 turns. No crossover winding. You don't need it. You don't want it. 14 gauge wire, not 12, and you've got to have a 200 picofarad capacitor instead of a 100. And you can put two 100s in parallel to get 200. The power rating on the thing is way over 2,000 watts. You have nothing to worry about there. And use 12 gauge wire for this antenna because that's a lot of wire. It will work on 75 meters just fine. You'll have a nice low SWR. It'll be a low loss system. It'll have a lower angle of radiation than the 80 through 10 version would. That's great for DX, but for local use, the other antenna would be better. Here's a picture of the transformer that I built. This is 3 turns and 21 turns secondary. 3 primary and 21 secondary. There's our capacitors. And I got a few FAQs here if you'd care to read through them. RFI, a lot of people bring this up as a potential problem for the end-fed half wave. However, with 9,000 plus members to the group, we just really haven't had many problems. If you do have an RF problem, it's likely because you ran your antenna too close to the house. We see that every now and then. Running the antenna over the house might set off your smoke detectors, but it would for any antenna. So we recommend grounding the coax, as you would with any antenna. Ground it before it goes in the house. And if you want, you can use a common mode choke near the shack or in the shack to try to keep any antenna currents off that coax. You can buy these chokes from DX Engineering and a lot of places. Myantennas.com has a really nice one that works great, and I have used that one. Right now I don't have any chokes at all, and I don't have any RFI. Who invented the antenna? Nobody takes claim for it. If they did, they're probably lying. The thing just cropped up somewhere in the Scandinavian area and traveled across Europe and migrated over to the U.S. by myantennas.com, and he makes great products. They're worth looking at. I don't think he's using 52 mix, but anyway, take a look at him. And there's also another brand in the Netherlands that's in Holland, actually, made by High Infed Company. And so just read down through these. We've got some suggestions here. And do you need a counterpoise? That always comes up. No, because older versions of the end-fed half-wave, a lot of articles recommended using a counterpoise, but it was a totally different design, and a counterpoise could be counterproductive on this design. You could actually end up radiating as much power from the counterpoise as you do the antenna, so do not use a counterpoise. And the power rating is another issue that confuses people, and that's why I just say go ahead and use the maximum 3-stack 52 mix cores and 12 gauge wire, and you'll be fine. Using less than that, using 43 mix and 2 cores or 1 core, you'll probably be okay with 100 watts with 1 core, probably 1,000 watts sideband with 2 cores. Sideband has a lower duty cycle than CW. 3 cores of 43 mix, you can probably run 1,500 watts on sideband and maybe 400 watts on CW on 80 meters and get by with it. But that's why we recommend 52 mix. Do not use tape on the transformers. That simply decreases the coupling between the wire and the core. Plus it traps heat, and plus it is not necessary. I have wound these things with bare copper wire, and there's nothing to worry about. Don't put tubing on the wire. Some people put tubing on the wire, Teflon tubing. There's absolutely no reason to do that. and it does increase the coupling, and that wire needs to couple magnetically into that core. That's what makes them work. So don't bother with it. Here's a summary of some of the nice features of the end-fed half-wave. The power loss is very low in the transformer. The ARRL laboratory tested them. They put two of them back to back and decided that they had about 1 dB of loss, and then you divide that by 2. So we're down around a half a dB. That's really less than a lot of good high-powered tuners have. Radiation pattern, of course, will vary depending on how you have it installed. And like I showed you here, it's expandable to 11 bands. Some manufacturers of end-fed half-wave antennas, we don't recommend the MFJ because of the way it's made. It's full of holes on one side, it leaks water inside, it's wound with cheap hookup wire, and they don't use the twist and so forth, so it's just not very good. There's a list of part numbers, and one comment here on the vent. I am now using this little funny looking vent on the top, and there's the part number for it. It's the same part number as the hooded vent, which goes on the side, but it's got an A after it, and the other vent has a B after it, so watch out for that. I'm putting this on the top, and the theory that I have is that the hot air goes to the top and will come out this way. Probably doesn't make much difference. There's my ground system outside, and it's pretty simple. Another view of it. Inside, I've got my two end-fed antennas coming in here to jacks 3 and 4, and this goes out to the station. It goes to an antenna tuner, which is usually in bypass mode, amplifier, and to the rigs. And my ground connection goes here. So if I disconnect this by simply pulling it off, this disconnects my entire station from the antennas and the ground. And that makes it safer, because if lightning hits your house and you've got all this hooked up, it will go through your house wiring, through your power supply, through your rig, and go looking for a better ground, and it's going to come through here and find this nice super ham radio ground that you put out here, which is better than what the power company put in. So it blows up your radios and goes out through this ground wire, and that's what happens. So I disconnect the entire station from both the antennas and the ground, and my station is just as safe now as the toaster in the kitchen. And that's the end. Thank you all for watching in 73.